these are the radioactive decay laws. And the first thing that I want to tell you is that they are obviously not true. Why do I say obviously? Well, these are continuous functions. We're talking about exponential decay. This is exponential decay. It's a continuous function. And that means it works not just for integer values, but also decimal values. It's going to give us integer values, decimal values, rational numbers, irrational numbers. It's going to work for all of them. But we're talking about atoms. Atoms only come in integer values. You can't have 1.273 atoms. You have 1 atom or 2 atoms or 100 atoms or 1,000,000 atoms, whatever. It's an integer value. So this is just an approximation. It's just a model. But when you have huge amounts of atoms, I'm talking billions, trillions, quadrillions, beyond that, this works extremely well. It's a very accurate model when you're talking about a huge collection of atoms. It only breaks down when you get a small number, but we're only ever going to be applying it to large samples, so we don't need to worry about whether or not it applies for our situations. It will apply. So let me get into the nuts and bolts of this. So N is the number of particles that, or I should say the number of atoms that have not decayed. N naught is what you originally started with. N is what you have after some time t. R is the decay rate. So R naught is the decay rate back at the beginning at t equals 0. R is the decay rate at some time t, after t equals 0, whatever you started with. It's exponential decay. Of course, we've seen this before. We saw it with the RC circuit. We saw it with the LR circuit. So mathematically, nothing new here. Now, there are a few more, you can see relationships, a few more symbols we need to talk about. So first, tau. When we were dealing with circuits, we called it the time constant. Mathematically, it still behaves the same, but we call it the mean life. When we're talking about radioactive decay, tau is called the mean life. And we call it the mean life because it's the average lifespan of an atom. So if I'm talking about uranium, it'd be the average lifespan of a uranium atom. Now, of course, mathematically, though, it still behaves the same as the time constant. That means, when t equals tau, okay, that means n is going to equal 0.368 n naught. And I can do the same for r. R is going to equal 0.368 r naught. Okay. So that mathematical behavior still there. Now this is the half-life. The half-life is how long until half of the original amount remains. So let me give you an example. Let's say I start out, and this is going to be an idealized example, but let's say I start out with 400 atoms. And let's say the half-life is 1 hour. Well, then 1 hour later, so after 1 hour, I should have, actually we just use H for hour, after 1 hour I should have 200 atoms. And then after another hour, because it's the half-life, it's how long it takes to get to half, then I should be down to 100 atoms. And after another hour, I should be down to 50 atoms. And I'll do one more after another hour. Hopefully you can guess what this is. 25 atoms. So that is what is meant by the half-life. It's how long it takes until only half remains. Now, both of these, the half-life and the mean life, tau, okay, we can get both of these off of the graph in a fairly straightforward way. So tau, we've already done. We already learned back when we were dealing with circuits with how to get it, but I'm going to go over it again anyway. So as we know, we know that when t equals tau, n is 0.368 of n naught, or r is 0.368 of r naught. Okay, so we'll just assume it doesn't matter if the y-axis here is n or r. It doesn't matter for the purposes of our analysis. So I'll look at right up here, this value right here, that's 3.8. Okay. 3.8 right there. Okay, so I take 0.368 of 3.8, and that's going to be approximately 1.4. So right here, this is 1.4. And so if I come down from 1.4, that's tau. Right there. tau is 5 seconds for this situation. Now, if I want to get the half-life, okay, I started with 3.8. How long to get to 1.9? 1.9 is going to be about right here. So right there. And so I come down, and this is how I would get it. Now, I can't get an accurate value here. I would guess that's about 3.5. That's just an estimation on my part, but that's how we get the half-life. So right there, this right there, this would be the half-life. Right there. Okay, now the last thing to talk about is gamma. Gamma is known as the decay constant. And notice that gamma is going to equal, and it's actually right up here. You can see tau times gamma is 1. So that means, of course, that gamma equals 1 over tau, which means that we can rewrite either of our decay laws as n equals n naught e to the negative gamma t. And obviously I could do it with the r as well. Gamma is useful because if gamma is much less than 1, then it tells us the probability that a given atom will decay within the stated unit of time. So let me give an example. Let's say that, for example, that gamma equaled 0.0, I'll say 0.097, and we'll make this inverse seconds. So that would mean, so I multiply that by 100, and I get that there's a 0.97% chance of decay every second. So for a given atom that has this gamma, there's a 0.97% chance of decay every second. That's what that would mean. Now again, this is only true if gamma is much less than 1 for that stated unit of time. If it's close to 1 or greater than 1, then you can't do this. It's not true. Last thing I wanted to point out here for the half-life formula, notice that we're not using E, we are using 2. So it's n naught times 2 raised to all this power. That's an important difference here. And this relationship here is a particularly useful one. It tells you the relationship between the original decay rate and the original amount of atoms that were present.